As we have seen before, Verilog can be used to represent a circuit in the RTL level of abstraction. So there are two fundamental ways of representing digital circuits in Verilog, which are structural and behavioral representation. Structural representation uses Verilog's gate level primitives to describe the logic operations. Various gate primitives like AND gate, OR gate, NOT gate, etc. are built in Verilog's gate library, and we can use them while describing the logic operations. So that would be the structural representation. Whereas in behavioral representation, we have to take the help of Verilog operators to describe the logic operation. Structural representation can easily become very time-consuming while designing larger circuits, and the behavioral representation is quite handy in those situations. In this slide, we will see how a logic function can be implemented in Verilog using structural representation. So once we are done with the module declaration, our first task is to express this relation in Verilog. Since this is an AND operation, we need to use Verilog's AND get primitive. The syntax for all get primitives are like this. First, we have to write the name of the output node, G, and the names of the input nodes that are to be specified. In this case, then X1 and X2. This line represents a two-input AND gate with X1 and X2 as input, and output is stored at node D. You can observe the synthesized logic circuit at the right hand. Now, for this part, we need an inverted input, so we can use a NOT gate, which will take X2 as input, store the output in Y. So we have X2 bar, and we can just AND it with X3 using an AND gate and store the output H. Now, T and H contain the results of these two AND operations. You can just simply pass them through an OR gate and store the final output F. Similarly, we can also use the behavioral representation to implement this function. As I discussed before, here we will use Verilog operators instead of gate level primitives. Here we perform the AND operation between x1, x2, and here another AND operation between bar x3. Finally, we OR them together using the OR operation and assign the output to F. So for behavioral representation, use Verilog operators. Now, a large number of operators are supported by Verilog. We will discuss them briefly in the next few slides. At first, we have the bitwise operators, which are used to perform logical operations on individual bits of the variables. Bitwise operators can be AND, OR, NOT, XOR, and so on. Next, we have the logical operators. They can operate on both single and multi-bit operands and produce false results. For example, this operation will produce a true result if either of A and B are at logic level 1, otherwise it will produce a 0 result. Now we have the arithmetic operators. As the name suggests, these operators are used to perform different arithmetic operations such as addition, subtraction, division, multiplication, and so on. Relational operators are used to express the value relations between two variables, whether one is equal to or greater than or less than the other. The result of such operation is one bit, true or false, like the bitwise operator. Here we enlist the remaining Verilog operators. Verilog, we have operators for shifting, concatenate, and replicate operations. We also have the conditional operator as described here. This block of code, we can observe the use of concatenation and replication operator in Verilog. Observe that this line represents a concatenation operation which concatenates D with the first 24 bits of E, and in this line we can see the use of replication operation. So here the sixth bit of D is replicated 32 times, and finally this 32-bit result is assigned to